Okay, so we're starting with some homework take-up. This is a nice question. I'll tell you right now, you can probably expect on the test some sort of thinking question that's going to involve a proof using a rewrite of vectors of some sort, like this. So prove that, so you're given this diagram, so again, just to make clear, we're told that A, B, and C are collinear. So we talked about what collinear means. It means they would all lie on the same line, and then the vectors on that line would be collinear as well. Okay? It says that B is the midpoint of AC. So that's important too, because you see that creates some equal vectors in this picture as well. Okay? Let O be any non-collinear point. So we throw O's anywhere we like, somewhere else. Prove that OA plus OC equals 2OB. Anytime you have to do a proof of something like this, your best bet, and just like with, like, for instance, I'll say two words that you probably are going to cringe, but I'm going to say them anyway, like trig identities. Okay? Anytime you have to prove something, usually pick a side to start with, like a left side, either the left side or the right side, and start trying to rewrite it so it looks like the other side. If I can take OA plus OC and start rewriting it so that it ends up looking like 2OB, that would be great. Or vice versa. If I start with 2OB and I can get it to look like OA plus OC, that would be great. I think it might be easier to go for make 2 become 1. Okay, so I'm going to start with the left side. Okay? So I'm going to go left side, and I'm hoping that last year, your grade 11 teacher, when you were doing, or grade 12 advanced function teacher, when you're proving an identity, you always start by just copying. Start with what the left side is. So the left side is vector OA plus vector OC. Okay. So let's start looking at doing some rewrites. So our goal is to get this to have OB in it, right? Is there a way to get from O to A that includes OB? Is there a way to get from O to A to start at O, end at A, but bypass through OB? Good. The OB plus BA, we can break it apart into those two, right? So we can say that OA is the same thing as OB plus BA. And you guys hopefully recognize, like, I won't always say the vector, but anytime you're writing 2 letters, it's with a vector on top. Okay, so vector OB plus vector BA. How about OC? Can I do the same thing? Plus is there a way to get from O to C that bypasses through OB? I could do OB plus BC. Okay, great. All right. Well, this is looking somewhat promising. Again, properties of vectors say I'm allowed to commute, right? Put vectors in either order. Would it make sense I could commute the middle two so that the OBs were next to each other? So I'm going to do that. So I'm going to go OB plus OB plus BA plus BC. So OB plus OB, 2 OB, 2 vector OB. Okay. Now, vector BA plus vector BC. So let's look at what those are. Vector BA looks like this. Here's vector BA, green vector. Vector BC looks like this. Now, I want to add those 2 vectors. Uh-oh, they're joined tail to tail. When we add vectors, we really want to join them head of first to tail of second, right? So if I moved the red vector to there, and again, human error, okay? Do we agree? What do we notice is happening here? You're going to get the 0 vector, right? They're just going to, it's like I go there, I come back. It's the same because of the fact that because B was a midpoint. That was the key, though. You had to recognize that B was the midpoint. So these vectors have the same magnitude, but are opposite in direction. But because they are the same magnitude in opposite direction, could I do a rewrite of one of those in terms of an equivalent vector? Like, look where I just moved the red. Could I just call BC the version that starts at A? Like, because those are equal, right? So you can even say something like, maybe I'll just write this for the moment, and you can say something like, since, like, do a little justification for yourself, since BC is equal to what vector? in the picture, is there an equivalent vector? I can move the BC somewhere else and it's also the same magnitude and direction. AB. Okay, therefore, I can continue. Okay, so maybe I'll just write equal. So I'm gonna actually do that replacement. Because look what happens when you do that replacement. You get that the lovely combo we looked at yesterday where the head of the first and the tail second match. So I can rewrite BA plus AB as BB. And a vector that starts and ends at the same location is just the 0 vector, which is, and then our identity rule says vector plus 0 vector is just original vector, which is the right side. So when I prove things, I like to do that. Have you guys ever seen that before? It's good old Latin, like it's quod erat demonstrandum, which means what was asked for has been demonstrated. So at the end of proofs, it's a nice thing to say, I proved it. It's basically like, it's like the equivalent in like ancient Roman times of like dropping the mic, like I did it. Okay, QED. Okay. Or you can just put like a smiley face too, if you prefer to be more modern. Emoji. Okay. So that's, now you might go, oh my gosh, Rich, you did so many steps there, but because I'm specifically asking for a proof, I'd rather you show me every intricate step than start doing all sorts of stuff in your head. Okay, I want to see the evidence of why you know it's true. Does that make sense, everybody? Okay. So vector proofs are going to look like this. Don't be shocked that they take like 8 to 10 lines because like you're doing rearranging, rewriting, and you don't want to do too much at once because I have to see the flow, right? You can't just go from here to suddenly there's only 2 vectors. I kind of need to understand what you've done. Okay. Any questions? Any other questions from 6.3? Yep. Number 5. So number 5. So that's the show that the copy the picture one. Okay. So it says copy vector u and then show geometrically that k plus m times vector u equals k times vector u plus m times vector u for k equals 2 and m equals 3 in various numbers. I'm just going to do one of them. Okay. So essentially what you need to do here is if you're going to do one of these, you have to kind of be on board with like, you have to measure it and actually be accurate or else it's not going to work. Okay? So if I choose, I did my best to draw my vector u here. I'm going to cheat on my smartboard and just start cloning it so I can refer to, I'm going to do clones of this. But on your, when you do this, if you do this on a paper, okay, if you do this on your paper, you're just going to have to do your best. Okay, I'm going to make this vector 1 centimeter so that when I draw 2 times vector, if I draw 2 times vector u, it's going to be 2 centimeters long, but in the same direction, etc. Okay? So this is saying that if I have, so if I'm just going to do A, or I want to do one more interesting. Should I do like B, because there's one's positive, one's negative maybe? I'm going to do B, okay? So B says, show geometrically that k plus m times vector u is equal to k times vector u plus m times vector u. So I'm showing the distributive property, essentially, I guess. One type of distributive property. So the goal now is to draw, and so for B, we want to let k equal 5 and m equal -1. So if I let k equal 5 and m be -1, does everyone see that the right side now is going to be 4 vector u, and on this side I'm going to have 5 vector u minus 1 vector u. Okay, I'm gonna leave it like that. I'm not going to simplify it because the whole point is to show this geometrically, not algebraically. Algebraically, can we kind of see this is going to be 4 plus -1 is 3. It's like adding like vectors. It's that same idea. But I'm going to leave it like this. So I'm geometrically going to draw the left side, draw the right side, and show that they're the same. So 4 times vector u. So if this is a vector u, I need 1, 2. My vector is kind of sad looking. It's a little curvy. Should I try and draw a better vector? I'm sorry, guys. Oh no. Okay. I'm going to be a little more precise. So I'm going to do this. Oh no. Okay. Delete. Okay. Usually when you lift the pen, down. Okay. So there, I'm going to do this. I'm going to put an arrow on it. Group those and make it a cloner. Okay. So group and infinite cloner. Okay. So now if I do 4 vector u, so 1, 2, 3, 4. Okay. So if I just draw a vector, right? Starting here, ending all the way there. Okay. Is everyone okay that this vector right here, that's 4 times vector u. Okay. Yep. Okay. So now, what's the right side going to be? It's me drawing a vector that's a 5 vector u. So 1 vector longer than this, right? And then I do. Okay. So now I do a vector that's 5 vector u's long. So there's my. Oh, there we go. Okay. Okay. So there's my vector that's 5 vector u's long. And then I'm going to draw a vector that's negative u. So how would I draw a vector negative u? Opposite direction, say magnitude is u. So if I draw a vector that's the same distance but just opposite in direction here, right? It's going to be like this, right? I'm just going to do it like right side by side, but technically it's on top. Okay? And then if I add those 2 vectors together, so it might have been better if I hadn't just done I should have just maybe left it like this. Okay? If I add those 2 vectors together, 5u plus negative vector u, I end up with a vector that starts at the tail of the first and ends at the head of the second. Is it all making sense, guys? Okay? And so this vector right here that I just found, I'm going to maybe change the color, make it orange. So this orange vector, do you guys get that this vector right here that I just drew is 5 times vector u plus negative vector u. That's the vector, or the orange vector. Is the orange vector, it's the same length, right guys? You all see how they're the exact same length. They're supposed to be the exact same length. Okay. They're exact same length. Okay. Human error, I apologize. But you get the idea. So if you're doing on your paper with centimeters, it should be exactly the correct distance because you've gone like a 5 centimeter minus a 1 centimeter should end up with a 4 centimeter, right? But that's the idea. And geometrically, you're literally showing me arrow pictures. It's not proving it algebraically. Geometrically means you're showing me drawings. Okay, fair enough? Okay. Okay, any other questions from 6.3? Okay, so this is the reason why, this is the main reason why we're not doing the quiz after 6.3, even though that's what it says in the outline, is because most of the questions, I think you would agree when you did the homework, is there's a lot of these ones where it's like you're drawing little arrows everywhere, and which are great, but they're not as convenient and easy to do, and you have to have a ruler and you have to be accurate for it to work. And the more applicable situation is to apply this to real life. And while there's been a few little real life scenarios that have kind of been dripped and dropped into the lessons, The 6.4 is actually a lesson where we go through applications. And that's gonna be an important thing on this test, is being able to apply the knowledge of adding vectors and scalar multiples of vectors and putting that idea together to answer questions that relate to real life. So that's what today's lesson is going to be all about. We're going to do some examples, some real life examples. And then the only thing left after this is going to be everyone, if you've taken physics, it's going to be your favorite lesson. It's going to be resolving vectors into rectangular components. You guys know what I'm talking about, physics people? Like you take a vector and you turn it into right triangles. You take vectors and you break it down into horizontal and vertical components.
It's satisfying to like write out, but it's like tedious.
Okay, so today we're not doing that, and I want to be very clear that unless I say resolve into rectangular components, I'd like you to be using the strategy I'm going to be teaching you today, which is just using sine law and cosine law in scenarios where it's necessary. Okay, so let's take a look at what we're going to do here. So we're going to apply what we've learned to solve real life problems that involve velocities and forces. This will involve using the Pythagorean theorem and trigonometry along with vector addition. So it's putting trigonometry and vectors and scalar multiples potentially too, all mishmashed together. Okay? So the thing I just said is two vectors that are perpendicular to each other and add together to give a vector v are called the rectangular vector components of vector v. Hello.
Any pictures?
I do not have any, no. Thank you. Okay. So let's take a look at this. So I guess I just lied. We're going to do a little bit of it today too. Okay, so rectangular components. So draw the resultant for each set of rectangular components. Then calculate the magnitude and direction of the resultant. So this one's a little different. Tomorrow it's going to be more, or sorry, Monday it's going to be more, here's a vector, resolve it into a horizontal and vertical. This one is, they're already a horizontal and vertical, make it a single vector. So it's like backwards. So a sailboat's destination is 8 kilometers east and 6 kilometers north. Your goal is to draw the resultant and then find the magnitude and direction of the resultant. You have the magnitude and direction of the two pieces, right? The two vectors. You have an 8 kilometer east vector and a 6 kilometer north vector. Our goal is to find the resultant. So where did the sailboat actually end up, right? Like if you're sailing, you're not going to sail east and then north. What are you going to do? You're going to go pick a bearing that gets you to where you want to go, right? And so the sailboat itself is going to start here at the initial position and at the final position. And our goal is to find the resultant. And the resultant will have a magnitude and a direction. In this case, do I need to use sine law or cosine law? The right triangle, and you're finding what side of the right triangle is missing here? The hypotenuse. So can we find the hypotenuse in a right triangle? We use Pythagorean theorem. Now, when you think Pythagorean theorem, what pops into your head? Pythagorean theorem is c squared equals a squared plus b squared, okay? Well, we don't want to use c, a, and b. We want to refer to the question right away. What is in the spot of c in this picture? The r. Now, I'm going to write something. I'm going to write, okay, resultant squared is equal to leg 1 squared plus leg 2 squared. And I'm going to tell you right now that if you write this on the test, you are going to get a mark off. Because you can never square a vector, because you can never square a direction. That makes no sense. You can't go like east, 40, whatever. You can't have a direction squared. It doesn't work. So anytime you do calculations with a vector that looks like this, you're doing the magnitude of that vector. So you automatically need to put bars around it anytime you're solving for the magnitude. If you're finding the magnitude, you need the bars. Okay? This is perfectly correct. This would be what I'd be looking for. Okay? So the magnitude of the resultant squared is equal to 8 squared plus 6 squared happens to be 64 plus 36, 100. The magnitude of the resultant is, now here's the good news, guys. What have I said all along? The magnitudes have to be positive. But when you square root, typically we have to always take into consideration a negative option. But I'm going to say don't worry about that for vectors. It's always positive, right? You're never going to have a negative magnitude. So what is the square root of 100? Just pick the positive one. 10. So you have found the magnitude of the resultant. You know how long it is. It's 10 kilometers. And please make sure you read questions, because sometimes in the homework it might just say find the magnitude of the result. Maybe you don't have to find the direction. Maybe just find the magnitude. Magnitude found. But if it says find the magnitude and the direction, I also need the direction. Where is the direction of a vector? It's always the angle that the vector makes at the beginning. It's never at the end. It's not where you're going. It's where do you need to head from the beginning for that vector to have the correct direction. So where should I put my, we're going to use theta as our go-to reference. So where should I put theta in this picture? There's like two places I could put it. I could put it down here, right? Or I could put it here, but what makes more sense? If I'm saying if you wanted to tell a person in the sailboat what direction to head, you don't tell them at the end of your journey, oh, you should have traveled this way, right? You want to find the angle at the beginning. So the theta we're referencing will always be with the tail of the vector. The angle will always be with the tail. The angle will always be with the tail of the resultant. Angle will be with tail of resultant. Angle will be with tail of resultant. Okay, so there it is. Can I find theta? I can. Do I need to use sine law? For right triangles, do we have a strategy for finding missing angles in right triangles? Good old friend Sokotoa, right triangles. You just choose the right ratio that relates the missing angle and the sides. Now, technically, you have all three sides now, but and again, this is just general rule. Hopefully, you've been taught this from throughout your high school, courses. That it's always better to use given info than info you found in case you made an error. So, can I come up with a ratio using the given side lengths, the 6 and the 8 and theta? What ratio would relate 6, 8, and theta? Tan, right? Opposite over adjacent. Does anyone need a trig refresher of opposite adjacent hypotenuse? We all know that. We're good. Okay. It's always the reference. The angle's your reference, right? So opposite is the farthest away. Adjacent is the leg next to it. Hypotenuse is always the longest side opposite the right angle, right? So if I want to find theta, so you can go tan theta equals, I'm actually fine if you just want to go right to town and go tan inverse. You know what I mean? I know I'm finding theta. So tan theta will be theta will be tan inverse of opposite over adjacent, 6 over 8. Okay, and so I grab my calculator. And again, make sure you're in degree mode now. For vectors, you're in degree mode. I feel like I need to put on the exam, like, you must switch your calculator to degree mode now. Okay, so you pass that page on the exam, right? So tan inverse of open brackets, 6 divided by 8 close brackets. Did you guys get 37 degrees? Okay. So the resultant is 10 kilometers. And then, so the 37 degrees is this angle right here. So legally, you can just go with the directions that are there, and using 37 as your reference, what would be what's your initial direction and where's the angle heading towards? East, 37 degrees, north. I'll take it begrudgingly, but the correct. But again, it is nicer to start with north and then go east. So could you find the equivalent vector that goes the other way? You just have to do what simple calculation? You just have to subtract from 90, right? So if you subtract 90 minus 37, 53, guys. So exactly the same answer. North 53 degrees east is also a correct direction, and it starts with north. Either of those, I will take them. Okay, as long as it's correct. Any questions on that one? Okay. So B, I'm going to do another one. It says, in a numerical model of the Bay of Fundy, the velocity of the water is given using rectangular vector components, 2.5 meters per second northwest and 3.5 meters per second southwest. Now, there's a big difference in this picture than the previous picture. Can anyone pick it out? There's a big difference in the way that picture looks. They're tail to tail. Look at the previous one, guys. They were lined up perfectly for addition. The head of the first and the tail of the second met. This one, they don't. Do you guys get that? That's not the picture. And here's like a clue. If you're ever saying, okay, I'm going to draw the resultant, and you don't, I'm like, I need to start at the tail. Oh, there's like two heads here, right? There's no tail to start at. You need to redraw this. And remember, we don't really care the order. You can redraw in either order, whichever one you want to put first. But you need to redraw it so that it's the head of the first is attached to the tail of the second. So on your paper, you might be able to just draw in. I don't know. I think you could. See, I'm going to go off the screen, so I think I'm just going to redraw it next to it. Okay. So if I redraw it next to it, okay, I'm gonna. Which one do you want to start with, guys? The 2.5 or the 3.5? 2.5. So if on your paper, I don't know if you have room for this, guys. You could just attach it over here and draw the resultant like this. Is this making sense? I'm gonna go over here, and so I'm gonna go. Here's my vector. Okay, there's my northwest vector, and then I'm gonna draw my southwest vector. And so there's my red vector, so I have a 2.5 meters per second northwest, and I have a 3.5 meters per second southwest, and then the resultant will be, if both those vectors had been 2.5, what do you think would have happened? If both those vectors had been 2.5 meters per second. What do you think the resultant would have looked like if they had both been 2.5 and that they're aligned northwest and southwest? They would have been, all vectors are straight lines, but they would be horizontal, right? Because it would perfectly balance, right? It would be going like a 45 degree up, a 45 degree down, and I'm going the same distance, creating a 90. Like I would basically be creating an isosceles triangle, and the tops would be both 2.5, and the bottom would be horizontal. So it should make sense that it's leaning a little to the negative because the longer vector will have more of an effect, right? Those vectors with those bigger magnitude will have more of an effect on the overall motion, right? Okay, so the resultant is here. So now our goal is to find the magnitude and direction of the resultant. The one thing to recognize is, even though I've redrawn it, is there still a 90-degree angle here? And this time the 90-degree angle. So you guys get that the original angle was here and there was the 90. By transplanting the 3.5 up here, I've created the 90 there. Does that make sense? So there's still a 90 degrees happening at the top. Okay. All right, here we go. So let's go for magnitude. So if it's a 90-degree triangle, can I still use Pythagorean theorem? So magnitude of resultant squared is going to equal leg 1 squared plus leg 2 squared. So leg 1 squared, 3.5 squared plus 2.5 squared. Again, this is where I'm fine with you doing a bunch of steps just on your calculators, guys. 3.5 squared plus 2.5 squared. I get 18.5. If you want to write it, you can. Okay. And then the magnitude of r, square root of 18.5 is, I'm getting approximately 4.3 meters per second. Rule of thumb is if they don't give you rounding rules, stick with the rounding given. Usually it's 1 decimal place for magnitudes and angles to nearest degree typically. So I found the resultant. Okay, now my question to you is, what should I be choosing for my angle theta? I obviously have to choose an angle in the triangle. So I have 2 options. I can pick the angle that's made with red purple or the angle made with green purple. Which one do you think I'm picking? If eventually the goal will be to find the purple angle, the angle that the direction of the purple vector, right? So should I be picking the angle that red purple? Yeah. So there's the angle I need to be looking for. You guys get that? Once I find this theta, I'm going to have to do some adjustment to it. But there it is. If I find that, then I can play around with it. Okay. So let's find theta. So again, notice that if I want to find the resultant, let's not use this. First of all, do you guys see in this case, it's really not a good plan because now you're going to use a rounded version. You're losing accuracy. Whereas those were exact. It's better to use exact versus approximate. So again, is it tan again? Yeah. Theta is going to equal tan inverse of opposite over adjacent. So what's the opposite of the theta, guys? 3.5 over adjacent 2.5. So tan inverse, open bracket, 3.5 divided by 2.5. I'm getting approximately 54. I almost want to go 54.5 degrees because it's almost halfway through that degree, but I'll stick with my rule of 1 degree, but the nearest degree. But it's 54.46. I might be tempted to just go 54.5 there, but no, I'm going to go 54. Okay, great. So I have my angle. So let's see what that means. So I have found that the angle here is 54. Okay. So now the question is, how do I relate that to north, south, east, west? And from a couple lessons ago, do you guys remember the fact that when you draw vectors, okay, it never hurts to put like your little bearings of north, south, east, west at the beginning of a vector to kind of just visualize what's the relationship of even the original vectors. Because that's all what we know. Right? We know the directions of the original vectors. We know that the red vector is on the northwest path. And what does northwest really mean, guys? It's missing. We don't typically put it in there, but when it's exactly northwest, there's an angle happening there. What's the angle between north and west? 45, right? You're exactly in the middle. That's what a northwest means. North 45 degrees west. So what they're saying here is, I'm just going to erase this blue just so I don't confuse myself. But if I draw my little north, south, east, west here, do you guys see? I'm going to even extend this a little further. Like, do you guys see my west and my north? The red vector is making a 45 degree with north and a 45 degree with east. The 45 degree with east is more useful to me. Okay, I know that from this vector here to the horizontal east line, what do I know that degree is? From this is the 45, right? To the east, right? North, this is like the east, that's the east line. So it's 45, I'm stopping there. Uh-oh, there's an extra bit. Guess what the extra bit is? There's an extra 9 degrees in there. Does that make sense? So I'm using a given angle, the 45. I then know that this little mini angle down here, right? That has to be 9 for it to work. So what I'm saying is, so when you get 54, even though 54 is my answer for theta, that's not going to be in my bearing. I have to adjust it. So I'm going to go 54 degrees minus 45 degrees equals 9 degrees. And now the resultant is 4.3 meters per second. And then what's the direction? Just use the 9 for the moment. So it would be, what's your initial direction? I'm sorry, I think I keep saying east. I meant west.
Yeah.
I'm sorry about it. That was bad. I'm like, oh, that's west. West. It's the 9 degrees. Like the purple vector. You want to find the direction of the purple vector. You need to start at a compass bearing. What angle 9 degrees is made with the west line? So I'm going to start going west. West 9 degrees south. Or what would be the equivalent if I wanted to start with south and end with west?
South 81.
Bingo. That's how you would state that one. Okay? That make sense? That's going to be the trick is figuring out when it's not as obvious, when things aren't lined up just automatically northeast and southwest. Okay? How does the finding a theta doesn't necessarily mean you found the bearing. You might have to do an adjustment. And the adjustment might require you to understand what's happening with the original angles. Okay, so now let's look at a different scenario. So first of all, a new terminology. It says an equilibrant vector is one that balances another vector or a combination of vectors. It is equal in magnitude but opposite in direction to the resultant vector. If the equilibrant is added to a given system of vectors, the sum of all the vectors, including the equilibrant, is the zero vector. So the picture there is trying to show you that if I add two forces together, F force 1 and force 2, and I get a resultant. If I then took the resultant and added the equilibrant to it, then the overall I would have a zero vector there. If I took the red vector here, right, and I said, okay, I want you to add this to F1 and F2. If I put that there, do we agree that then the overall would have a zero vector? If I take resultant plus equilibrant gives you 0. How do you get, so that's another way of saying is F1 plus F2 plus equilibrant gives me 0. This happens a lot. I'm sure this happened to you, but anything that's like suspended from the ceiling, okay? You guys, like if you put in your homes, I'm sure you have like some sort of like chandelier or like some sort of light fixture in your ceiling, okay? You guys get that in order for that to stay in place, okay, you have to have forces holding it up, whether it be like, you know, the brackets holding it to the ceiling of some sort that are holding it in place, i.e. having some sort of tension or having some sort of force to hold it in place to counteract the force of gravity, right? Or you guys are, you know, when you were back in elementary school and your probably teacher's like, go get the TV from next door, and you would go, you'd be so excited, you go with your friend and you go push the TV, but then, you know, one of you's pushing and one of you's pushing from the other direction, and you can basically, if you both could be exerting a force, but it could be the case that the television's not moving or the cart's not moving because you're working against each other. You're applying a force that's equilibrium, right? So you're pushing one way and the other one pushes back the same force, then the result is zero movement, zero force. Does that make sense? So that's the idea here. So let's take a look at a couple of examples. So a clown with mass 80 kilograms is shot out of a cannon with a horizontal force of 2,000 newtons. The vertical force is the acceleration due to gravity, which is 9.8 meters per second squared times the mass of the clown. Find the magnitude and direction of the resultant force on the clown, and then find the magnitude and direction of the equilibrant force on the clown. Does that make sense? So we're going to find the resultant And then when we get a resultant, the equilibrant will just be the same magnitude, but what's the direction going to be? Same magnitude, direction will be opposite direction. Okay, same magnitude, opposite direction. So let's find A. A has nothing to do with equilibrium, it's just find the magnitude direction of the resultant. So let's find the resultant. So let's draw what's happening here. No picture provided, we got to do it DIY, do it yourself, make your own picture. Okay? So a clown is shot out of a cannon with a horizontal force of 2,000 newtons. So what should my first vector look like? Horizontal force. Okay, so horizontal force, 2,000 newtons. So there's my clown initially. That's the force the cannon is applying to the clown. It moves 2,000, its force is 2,000 newtons horizontal. Vertical force is acceleration due to gravity, 9.8 meters per second squared, times the mass of the clown. So typically, vertical force or gravitational force, a lot of times, I don't know if in physics you called it G with the arrow on top, or F, capital F with a little g for gravity. Is that better? Okay. So now I'm going to do something here. So they're giving me a formula here. They're saying that the magnitude, so the force due to gravity is calculated by multiplying the mass times the acceleration due to gravity. Now, right now, there's all sorts of things wrong with my equation right now. Because right now in this equation there are vectors, and I can't multiply vectors. I can't. It just doesn't work. I can do calculations on my calculator with magnitudes of vectors, but not just vectors. So there's two vectors in this. I should be writing it bars around both of them. Does everyone get that the m doesn't get bars because the m is just the mass? It's already going to be positive. It's a scalar, so you don't have an arrow on m. So you have arrow on force and you have arrow on acceleration due to gravity, because both of those have a direction attached. You guys get that the force due to gravity will have the same direction as the acceleration due to gravity down. So there's directions attached to those. The mass, that's just a number. So they give us that number. They tell us that the clown is 80 kilograms. And the acceleration due to gravity is 9.8. And 80 times 9.8 is 784. And the result is a force, and forces are measured in newtons. Okay. So now, going back to my picture, I can now add this force to the force of the horizontal force applied to the clown, because you guys get, as soon as the clown leaves the cannon, it's really no longer going horizontal, right? Because what immediately after it's out of the cannon, what's now going to be affecting the trajectory of the clown? Gravity, right? Gravity is going to be aiming it hopefully towards some sort of net or padding of some sort, but there's some sort of, trajectory of going down. How do I account for that? There's the force that's accounting for the force due to gravity. So the vertical force, 784. Now, this is where I'm not going to be on your test paper being like, okay, time to see my ruler and make sure that if this is 2 centimeters, this is 7.8 centimeters. You know what I mean? Technically, that would be a good plan, because that would make your picture as accurate as possible. But I'll give you some leeway that you can freehand it a bit, but if you do so, just try your best to keep things in proportion. So what I mean by that is, if I'm about to add a 784 newton to a 2,000 newton, I better make sure that this force is less than half the size of this one. Does that make sense? Because half would be 1,000. A quarter would be 500. So you see what you have to play the game with making it proportional, or else you're going to get an answer that numerically might be something and doesn't look like it on your picture because it's not to scale. So if you have the time and you're feeling good about it, and you're have that artistic quality, and you're being exact, if you literally said, okay, I'm going to let 2 centimeters be 2,000 and 7.8 and 0.78 centimeters be this, you could draw it to scale. Or you could just say, okay, that's 2,000, so that's halfway, so I'm going to make my down less than halfway. You know, that's a good approximation. Okay, and this is where when you're on your paper and you kind of start doing this whole thing, I'm sure you've all done this before. Okay, that's, you know, you play around with it, like, did I make it long enough? Did I make it a little longer, shorter? Just make sure you can kind of, you've done it approximately to scale. And then now we can draw the resultant. In this case, because we were dealing with a horizontal force and a vertical force, I created what type of triangle? Created a right triangle again. Okay, so we're going to do it a third time today. So now we're going to find the resultant magnitude and direction. Okay? So magnitude. So resultant square, magnitude of resultant squared equals 2,000 squared plus 784 squared. I'm honestly completely fine if you just do everything on your calculator, square root, give me answer. I don't need to see a bunch of steps for these ones. So 2,000 squared plus 784 squared, and then I square root the result. I got 2,148.2 newtons. Okay, now I'm going to go for direction. So again, where should I? What theta should I be solving for? The theta near the what of the resultant? Near the tail. So we want the angle near the tail because that tells me the direction my vector should be going in. Okay, so I'm going to find theta. Good old tan inverse again. What's opposite theta and what's adjacent to theta? Opposite is 784. Adjacent is 2,000. So tan inverse, open bracket, 784 divided by 2,000 is 21. I'm really tempted to write 0.4, but I'll just write 21 degrees. Okay, and then, so the resultant is 2,148 newtons. And then what's the direction, guys? So the theta, in this case, you didn't have to do any adjustments or find any extra angles because the theta is an angle that's made with what direction? With, it's not with east, you gotta be careful here, with the horizontal. Okay? So we have to maybe be a little, you guys get, you can't turn this into a east-south because that's not how the clown's moving. The clown's just going horizontal, vertical. So we need to go back to, remember the very first one way without compass bearings is just an angle clockwise or counterclockwise with the horizontal. Can I say something to that effect? Okay, the resultant is 2,148 newtons. At an angle, I'll say 21 degrees, and so we're going to say clockwise or counterclockwise to the horizontal. Does the theta go, or I can say at 21 degrees below, I can even say below the horizontal, maybe that even makes better sense in this context. Below the horizontal. Okay. For the equilibrant force, you guys have to do zero work for the equilibrant force. After all the work's here, okay, the equilibrant force is, in terms of magnitude, is it any different? Same magnitude. Do not make that negative, I will be very sad. Okay, magnitudes are never negative, so just say same magnitude. And then, in terms of the direction, if the resultant is going 21 degrees below the horizontal, what do you think the equilibrium has to go at 21 degrees above? So again, what that means visually would be if I drew the result, the equilibrium, if I started here, right, and okay, let me try again. Okay, so if I draw the equilibrium, it's really bad. It's Friday, guys. My line bar is sad. I'm gonna try this. That's as good as I get. Okay, so there's my equilibrium. Do you guys get that? There's the horizontal, and do we all see kind of, that would be the 21 above the horizontal. And I'm just to kind of recognize, you guys see the Z pattern, like all these things with parallel vectors and stuff, you can kind of play the game with that to kind of find these angles if you're not sure. Okay? Good so far? Okay? So, yeah, the last two examples, we'll see, hopefully we can get through them. So the last two examples are probably the most applicable to real life. Okay? We don't see clowns getting shot out of cannons on a daily basis, but planes fly around the country on a daily basis, or boats travel on water on a daily basis. And, you know, you have tensions holding things in place, forces working on objects on a daily basis. So the next few couple of examples are going to kind of focus in on a real life situation and how to find a force or find a resultant velocity or find a resultant force. So a heading is the direction in which a vessel is steered to overcome other forces such as wind or current, with the intended resultant direction being the bearing. So the idea here is you plan to go, if you're traveling somewhere and you know, it doesn't only happen in cars, but it happens on anytime you're going to be traveling in a vehicle or in a mode of transportation that either wind or current could affect your motion. You have to adjust for that when you aim your boat or you aim your plane, right? Like, so that you end up where you need to, right? If you're in a plane and you're like, I need to go from Toronto to Niagara Falls, if you just like set course to Niagara Falls and don't pay attention to the wind, and you just go, okay, I'm going to Niagara Falls, and you just aim there, the wind's probably going to bring you off course, and you're going to not end up in Niagara Falls, you're going to end someplace else. Whereas if you say, okay, the wind is going to affect me in this way, so I'm going to head in this direction so that the wind takes me back so that I end up going to Niagara Falls. That's called adjusting your heading so you end up going on the correct bearing. Does that make sense? So you point your plane on the heading. Like the head of your plane is going in the direction you want to go. The result will be where you end up going. And that will be your bearing. Okay? And then the wind or current will adjust the heading so that you get to where you need to go. And so another way of thinking of this is from the perspective of ground velocity and air velocity. If I'm in my plane, okay, and I'm traveling, and like on my plane, it's going to say, my plane is moving at this velocity. Okay, I have this certain velocity. But because of the fact that the wind has a certain velocity, from the perspective of the ground, I'm not actually going that velocity. I have a resultant velocity from the ground's perspective. Is this making sense, everybody? So that's the idea here. When you're given questions involving plane travel or boat travel, the idea is you're going to draw a picture, and usually it's you need to get here, what bearing should you be, or what heading should you be on, or if you go in this heading and you follow this wind, what would that resultant be? Let's see what the first example says here. It says, an airplane is flying at an airspeed of 500 kilometers per hour on a heading of 040 degrees. A 150 kilometer per hour wind is blowing from a bearing of 120 degrees. Determine the ground velocity of the airplane and the direction of flight. Okay, so in this case, they're telling us the plane's speed and heading. So the plane's velocity Okay? You guys get, that is the plane, I'm in the plane and I'm aiming in a certain direction and I have a certain speed. I'm from the plane's perspective, that's the info. That's one vector. Okay? A 150 kilometer per wind is blowing from a bearing of 120. So I now have a wind blowing from a bearing of 120. That's going to affect where my plane actually goes. Find the ground velocity. From the ground's perspective, where does this plane actually go? You have to take into consideration both of those vectors. Is making sense? Okay. Now, there's a word in this problem that messes up so many students, and it's a really tiny word, but it's very important to pay attention to. And it's this word right here. If the wind is coming from a certain bearing, it's actually going in the other direction. Does that make sense? If I say wind is coming from the east, if wind's coming from the east, where is it going to push you? It's going to push you west, right? It pushes you the opposite direction. So you have to be very, very clear. If it says, and wind is blowing towards a bearing, if it's towards a bearing, then all good, you just take it as it is, that's the direction. But if it's from, you have to take the opposite. So if I draw this, so let's start with the plane. So it says the plane is flying at an airspeed of 500 kilometers per hour on a heading of 040 degrees. So as soon as you see a heading looking like this, remember we learned two types of bearings, right? Remember we learned quadrant bearings and true bearings. Good hint. True bearings. True bearings are when you don't have any north, south, east, west. You just have a 3-digit degree. And what did we say that means? That's a reference to north and which direction? In which direction from north? Clockwise from north. So what is this really? If it helps you can turn it into a quadrant bearing. What's 40 degrees clockwise from north? North. 40 degrees east. That's the bearing. So that's the heading, I should say. So I'm going to draw. So don't start right at the edge of your page. I'm going to start right around here. I'm going to do this first. You guys see what I'm about to do here, why I did that first. I need to have a reference of north, south, east, west, northeast, southwest, so that I can draw this vector correctly. I'm about to draw a vector that is north 40 degrees east. So I'm about to draw north 40 degrees east. 45 would be perfect diagonal, so it needs to be a little bit less than perfect diagonal. I'm not saying you have to grab your protractor. If you do, yay you, but you don't have to. But as long as if this is the 45, I need to make sure my vector is less than 45. And I'm going to say that distance I've just chosen here, this is a 500 kilometer per hour vector. And I'm going to label, and this is where it's going to be important to label your diagrams. I'm going to label this with a 40. That's fixed. North to red vector is a 40-degree angle, non-negotiable. Okay? Now, the wind is blowing from a bearing of 120. So guess what I'm going to draw at the head of this vector? Guess I'm going to draw another one of these things. Because now I need to draw a wind coming from a bearing of 120. Let's first figure out where is 120. If it helps you, from a bearing of 120, bearing of 120 would be, remember 90 would be east. So where's 120? An extra 30 degrees. East 30 degrees south, right? Or south 60 degrees east. Remember, that's what a bearing of 120 is. But that's where it's coming from, not where it's heading to. I need the exact opposite of this to draw. When I draw my vector, it's the exact opposite of this bearing. So what's the exact opposite of that? The exact opposite of east 30 degrees south is west 30 degrees north. West, 30 degrees north. Make sense? So I'm going this way. And don't make it too long because it's only 150. So 150 is around like 40, you know, like it's 500. You want the red to be 500. 150 is less than half, like 250 is half. So it's got to be quite small, okay? And so I'm going to just leave it there, and I'm going to call this 150 kilometers per hour. And I'm going to put my 30 degrees right there. There's a 30-degree angle right there. Okay. And now I'm going to draw a green resultant that goes from tail of first to head of second. And that's the resultant. And the resultant in this case is the ground velocity. Okay? So from the perspective of like the control center on the ground of this plane, it's going on, if they're measuring like the flight control center, they're saying that's where the plane's going, green direction. Okay? From the plane's perspective, it's aiming in this red direction, but the wind is pushing it into this direction, so it ends up going in the right path. Is making sense, everybody? Okay? Once the picture is there, now it's all about coming up with what strategy to use. So you guys get, this is very similar to the one we did way back way back 2 days ago, way back on Tuesday or Wednesday, which was the one where we had to use, remember, cosine law and sine law. And the idea here is, I have two side lengths. I know 500 and 150. And what was the rule? I'd love to know the angle in between. Every time you do one of these, when it's set up like this, the angle in between, it might not be given to you, but you can find it. So take a look at what we know. We know part of this angle right here. I'm going to color it in blue here. You guys get, we need to know this blue angle. Do we know part of it? The purple part is 30. Yes? How can I find this part down here? I want you to understand that this part here that I'm coloring in blue at this moment, okay, it's an angle made with the east-west line, or the horizontal. Is there any other picture in this triangle? Now go focus on the whole picture, that where you see the same vector, the red vector, making an angle with a horizontal. Down at the beginning, right? So now 40 was the angle made with the vertical. That's not helpful. But do I know what the red vector makes with the horizontal? It makes 40 with the vertical, with north. It means it's making what angle down here, guys? 50. And then, good old Z pattern, alternating angles. If that's 50, won't that little bit be 50? Just this little bit. So that the total angle at this point here, the total angle there, do we see, is going to be 80. Okay? So like the angle between the two vectors, right, is 80. You don't have to write it in words. If you just go 50 plus 30 is 80, somewhere around here, that would be fine as well. And you guys get, I did a lot of writing up there just to show you things, but if you somehow just went like, you drew this and then you went, that's 80, like that's okay too. Like I just need some indicator that you know where the 80 is coming from. Okay, it's 80, not 90. Wah, wah. So I can't use the strategy that I did for all the examples today. I could use the Pythagorean theorem strategy for all of these because it was always a right triangle. But now the angle I know is an 80-degree angle, so I have to use cosine law. So remember, resultant squared equals. You don't need to write the generic cosine law. Okay? You just have to use it. So remember, the cosine law says, okay, I'm just going to write it up here. C squared equals A squared plus B squared minus 2AB cosine of angle C. That's the rule. I don't want to see it as part of your solution. If you want to write it at the top of the page, that's fine, but I don't want to see it as part of your solution. Just use it. So the resultant is your C. And then the A and the B are just going to be the magnitudes of the other two sides. So I'm going to go 500 squared plus 150 squared minus 2 times 500 times 150. Cosine of angle between, we found that angle between to be 80. Magnitude of R equals, so I'm fine with you going type, square root answer. I don't need to see like 10 lines here of you simplifying this, right? So 500 squared plus 150 squared minus 2 times 500 times 150 cosine 80 equals square root answer. I just got 496.4 kilometers per hour. Does that seem reasonable? My plane is my plane's engine says I'm going 500. The wind is taking me off course a bit, so it's going to adjust my velocity. But the wind is so much smaller related to mine. It's affecting it a bit, but not a lot. And it's not like it's working completely against me. You guys get, like, if the wind was coming like at you and it was causing you to almost go backwards a bit, then your velocity would be even more affected. Do you guys get that the wind is actually helping a bit too, right? Because it's aiming a little bit towards where you want to go as well, right? Okay, so that's good. Now that I have that, I also need my what else do I need? I need the direction I'm traveling in. So again, where should I put my theta here, guys? The theta I want is the angle the resultant makes at the beginning. So in this case, we drew the picture. It's going to be the green vector with the red vector. So I want to find this angle right here is theta. Don't be fooled. It's not 40. Does everyone see what I'm talking about? It looks like there's a 40 there. Oh, it's already there, 40. No, that's what's north. You guys see the green vector isn't going north. So you need to find the angle here. I'm going to find this angle, and you guys get the angle I'm going to find is not going to be with north or east, but once I know it, can I use the 40 to help me find the angle with north? So that's everyone seeing how this works? It's all about playing with the numbers and looking at what you know and what you need. So if I find theta, then we're going to use sine law. Okay? So sine of theta over its opposite side. So again, the sine law, right? Sine A over A equals sine B over B. Sine theta over, what's the side opposite theta in this picture? What's the magnitude of the side opposite theta? 150 equals sine, I need an angle side pair. You only have the one angle, 80. You have to use the side opposite it. You have no choice. You have to use the number you just found. 496.4. And again, you do as much as you can in your head. If you need to, you could go, I typically, if you want to write this, sine theta will be 150 sine 80 degrees over 496.4. Does everyone see what I'm doing there? I essentially just brought 150 up with the sine 80. Or you just say, you isolate this by doing multiplying below this times this divided by this, and then sine inverse. Sine inverse, I don't even need to see the sine inverse here. I'm just going to go, what is the theta? Looking at the time, the bell's going to ring in a second, guys. Just give me 1 second. So 150 sine 80 divided by 496.4 sine inverse. I just got 17 degrees. So you now know that 17. Could you then adjust to find the north angle to the east that we're going to go? That's what you would do. We'll finish this up, but guys, I'm going to give you a subset of questions from 6.4 to do. And then on Monday, I'll give you the show what you know once you've practiced and we finish the lesson. So we're looking at finishing the lesson Monday and working on a show what you know. Tuesday will be the last lesson. Wednesday review, Thursday test. I think that's the plan. Okay? If you come talk to me if you think Thursday is not going to be doable, we can try and come up with an alternate arrangement so you can write beforehand. Thanks for listening. Bye for now.
Man,
Yeah.
I'm still really confused.